Okay, so let's begin. So we saw about Archimedes' principle last time. That upthrust or buoyant force equals to the weight of fluid displaced. So let's apply that to floating objects today. So floating object is one where basically the buoyant force is able to balance the weight of the object. Okay, because comparatively the object's average density should be less than the density of the fluid in which it is placed. Let's say this is an ideal fluid of uniform density rho. So then for such an object, the buoyant force exactly balances the weight. So we have the relation that the condition for an object to float that is given by this. Or in other words, we can say density of the fluid multiplied by the volume of the submerged part into G is equal to mg. So in case the body which is floating is of isotropic nature, that is, it has a uniform density. So if the floating body is a solid material, a solid body of isotropic or uniform density, say rho, and volume V. So we can write the mass of the object as the uniform density into the volume. So then we get the relation that buoyant force equals to mg will further imply that the density of the fluid into the submerged volume into G is density of the solid material into total volume into G. So we get this other relation that the fraction of the volume submerged is equal to the relative density of the material with respect to the fluid. But remember, this will only be valid when we can write the mass as density into volume. So for that, it has to be a solid body of uniform density. The first equation is universal for any and every type of body which is floating. The second one is conditional, that the body floating should be solid and of isotropic or uniform density. Just okay. So as a simple direct consequence of this equation, we can see, for example, that a floating iceberg density of ice is 0.9 gram per cc. Density of pure water, of course not saline water like sea water, but I'm saying pure water, is 1 gram per cc. So a floating iceberg has 9/10 part of its volume submerged. So very large fraction of an iceberg is submerged, something that causes icebergs to be very dangerous because it's difficult to visualize. Of course, nowadays with technology and infrared sensing as well as radar, etc., it's not difficult at all to do the imaging of the entire iceberg. But visually from the surface of water, it's very difficult to estimate the size of the iceberg and what part of it is submerged. Okay. Okay. Now let's see a different type of example. Now we have this thing. We have, let's say, a spherical shell, okay, made of something like rubber or plastic or something. Now it happens to be floating in water with 50% of its volume submerged. But it's not a solid sphere. It's a hollow shell. So I'm coming to that. So this is water of density 1 gram per cc. Now this is a rubber ball. So the rubber ball is actually a thick shell of solid rubber. This is of density rho of inner radius, say R1, equal to 5 centimeters, and outer radius equal to 10 centimeters. So you want to find the density of rubber. So from this density, so this rubber ball floats with 50% submerged. So you want to find the density of rubber from this information. Okay, so if you cut that rubber ball, its structure looks like this. It's a thick shell of rubber. It's hollow from inside. It's a thick shell. It's a spherical shell. Okay, so let's see the concept applied in this question quickly. So the buoyant force should be equal to mg. So the buoyant force will be equal to density of water into the volume submerged. So that will be 50% 0.5 of the outer radius cube 4 by 3 pi r cube. Whereas this will be density of rubber into the volume of rubber, which will be this. Okay, this is the volume of the solid rubber part in this whole thing. So now you have to use this density of water into R2 cube will be equal to density of rubber into R2 cube minus R1 cube. Now you can see that R2 is equal to 2 times R1. Okay. So therefore density of rubber will become 8 by 7 times density of water, or 8 by 7 gram per cc. So very simple type of question, as you can see. Okay. No, Aman, hope you have understood why it is not 0.5 and it is 8/7 instead 0.57. It would have been 0.5 had it been a solid sphere. You understanding the point now? Okay. Now the other interesting thing, yeah. So Aman, I hope this point is clear now. Okay. Now supposing in the same problem we had little bit more complexity, like the portion submerged was not exactly 50%, but it was up to something like this. You know that we know the outer radius was 10 centimeters and the portion that was outside water is visible to be a certain distance which is given like this. The portion which is outside water, this was something like, let's say, 3 centimeters. Okay. Then the thing is we would have had to involve integration to find out the volume submerged. So the same question, suppose this was the case, okay, that this is, now let's say this is a solid rubber sphere. Okay, of radius 10 centimeters, density rho, and this is of course water of density 1 gram per cc. Now in this problem, I want to find out the density of rubber. So what I'll have to do is I'll have to calculate volume of the submerged part. Okay. So in this case, because it's a solid body, when we equate buoyant force equal to mg, we will see that density of fluid into volume submerged into g will be density of the material into total volume into g. So we'll be able to calculate the density using this relation, that density of rubber upon density of water will be equal to the volume of the submerged part divided by 4/3 by r cube. Now the question is, what is the volume of the submerged part? So for that we have to use integration. So for that what we can do is, just like we did derivation of spherical volume using integration by slicing it into discs, same thing we can do here. Okay. So let's say at a vertical distance of y, we will slice a disc like this of thickness dy and radius r. So this is really a disc like this. Like this. This thickness is dy. So this disc has a volume of pi r square dy. Okay. And of course, from this diagram, you can see that the relationship between small r, capital R, and y is that they form a right angle triangle. Okay. So you can see that r is square root of this. Okay. So the volume of that disc So now the volume of the submerged part, what we'll do is we'll integrate for all the discs which are underwater. So that will become from y equal to minus this thing, minus 10 centimeters below, to y equal to plus 7 centimeters above, because 3 centimeters is above water. And of course, we understand r is 10 centimeters. Okay. Or we can also write this as y equal to minus 10 centimeters is minus r, and y equal to plus 7 centimeters is plus of 7/10 r. You can also write it this way. So this becomes Oh, sorry, there's a by 3, my mistake. So this calculation will be a little bit more complicated. So whatever this factor is going to come now, we will substitute it in the above equation of flotation, and from that we'll get the density of rubber. So this is slightly more advanced type of question where the calculation of volume of the submerged part involves an integration application. So it's about 1.25 pi r cube, or approximately 5 by 4 pi r cube. Okay. So this ratio from above you can see becomes so density becomes okay. So that's another type of question, as I told you. Now another type of question we have a solid wooden cube, okay, of dimension L by L by L, and mass equal to, let's say, 5 kg, which floats in water with 60% of its volume submerged. Okay. Now, a metallic object of mass m prime is placed on the floating block. Find the maximum possible value of m prime such that the block still floats. And in the second part, the floating block is attached with a rubber block So in this case, we are taking a type of rubber which has more density. It has a density of 4 gram per cc. Okay. Density of water, of course, we'll take as 1 gram per cc. So find the maximum value of x such that the block, which is formed of rubber plus wood, floats. So in this case, what we have done is the rubber block is attached with either from above or below, it doesn't matter. Okay. Sorry, the wooden block is attached with a rubber block like this. So this is the two-dimensional side view. Now you want this combination to float. Okay. So when you place it in water, in general, it would be something like this, the level of water. So the rubber is attached, okay. Whereas in the first part, you want a situation like this. You have just kept a solid metallic object of mass m prime like this. You placed it on top. It's not really attached in that sense. So the wooden block has to float in this manner. Okay, so this also, I mean, comparatively, you will see it's quite an easy type of question. You just have to work out a sort of inequality relation. Yes, Kevin, the first part's answer, correct. Aman, check your answer again for the first one. So see, first of all, from this information here, you'll understand one thing, that the density of rubber, the density of wood is equal to how much? It's 60% of its volume is submerged and it's solid. So it is 0.6 gram per cc. Okay. So in this case, if it is just about floating, the limiting condition is that the volume submerged should be less than equal to the total volume of wood. So this is the limiting condition. Okay. So for the first part's answer, the volume of wood submerged should be less than equal to the total volume of wood. Okay. So density of water into volume submerged into G should be equal to M prime plus mg. Okay. So 1 into V submerged into G should be equal to M prime plus 0.6 into V into G. Okay. And we also know that this 0.6 V is equal to 5 kg. Okay, so we have this information. So we'll make use of that. So V submerged is equal to in CGS unit, okay, where this is in cc, and so this should be less than equal to V. So that means M prime should be less than equal to 0.4 V. Okay. Now we know that 0.6 V is equal to 2 kg. Therefore, 0.4 V is equal to 4 by 6 of 2 kg. So this becomes answer. Yes, Nikita, that's correct. Naman, I think just you've forgotten to cancel the factor of G, is it? No, something wrong with your solution. Okay. Kevin, you have also forgotten the G factor, is it?
So 0.62 is equal to 5 kg. 2 kg.
Yes.
Yes,
Oh,
sir.
sorry,
It's not
sorry,
2.
sorry, my mistake, my mistake. It's not 2 kg, no, it's 5 kg. Okay. So this answer will come out to be different. Okay. So the mass of the wooden block, okay, which was density of wood into V, this was 5 kg. Okay. So therefore, 0.4 V will be equal to 5 into 4 by 6. So that's yes, 10 by 3. Yes, my mistake. This is 3.33 kg. Okay. Yeah, so Kevin, your answer is correct. Aditya correct. Naman also correct. But Aman and Nikita, you have to check your answers. Okay. Now the second case is somewhat different. Okay. This was the first case's solution. The second case's solution is somewhat different. Here you can see what is happening. That you have more buoyancy available to you because the rubber part is also having a significant volume, and because the rubber is attached to the wood, so it it can be part of. In fact, the rubber could be attached from below also or from above also. It doesn't make a difference. Okay. So the calculation is a little bit more intricate. The formula for your maximum buoyant force will be the total volume into density of water into G. So total volume will include the volume of rubber also. Okay, so let's come to the second part. Yes, Aman. Understood. Uh, the rubber attached. Now, for the limiting condition where it's just about floating, the level of water just about reaches the top. In this condition, you can see that the volume submerged is less than equal to L cube plus L square x, where this is x. Okay. So the buoyant force, the maximum buoyant force we can have is density of water into this. So the maximum total weight is going to be equal to this maximum buoyant force, or in general, so the weight is going to be density of wood into L cube plus density of rubber into L square x into G. It should be less than equal to this. So this is the condition that we get. Okay. So 0.6 L cube plus, now how much was the density of rubber that we had taken? 4 gram per cc. So 4 times L square x should be less than equal to 1 into L cube plus L square x, or 0.6 L plus 4x would be less than equal to L plus x. So 3x should be less than equal to 0.4 L. So x should be less than equal to 0.4 by 3, or that is 2 by 15 L. And from that, now we can find out the maximum value of x only we wanted. So that is, so just check my calculation once. Okay. Rest, this is the method. Yes, Vaishnavi and Aditya, you got the same thing. Okay, Smikita, I'll just take you back to the first solution. Just compare it once more. See, the thing is you have to get the answer independent of L now. Okay, good. Okay, now next very interesting concept. Just like we have center of mass and also center of gravity. I think you people would have learned about center of gravity by now because we're studying gravitation. So you'll see that in a uniform gravitational field, the center of gravity is basically the center of mass, because whatever is the symmetry point for mass, the net gravitational force will also act through that point only, because the gravitational field is uniform. So, like that. So now, like that concept of center of gravity for the weight, there's also a concept of center of buoyancy or buoyant center. Okay. Center of buoyancy or buoyant center, it is like the point through which the buoyant force acts. It is the effective point through which the buoyant force acts. So, for example, if I have a body like this completely submerged in fluid, now you know that the buoyant force is actually acting as a distributed force, because there is force due to pressure acting here, little bit larger force due to pressure acting here, and force due to pressure acting like these vectors. But the resultant of all this is the buoyant force. So the effective buoyant force in this case will act through the centroid of this. So the point through which it acts, let's say we call that CP. So in this case, the buoyant center is the centroid of the submerged body, the fully submerged body, because basically the center of buoyancy is the center of gravity of the equivalent weight of water displaced, or equivalent weight of fluid displaced. So whatever the shape of this sunk object, the fluid it has displaced is a fluid of that much volume but of uniform density. So its center of gravity will be at its centroid, geometrical centroid, because it doesn't matter, the body itself may have variable density, but the fluid it has displaced, it was an ideal fluid, so it's a certain that much volume of fluid which is of uniform density. So center of gravity of the equivalent weight of water displaced will be the centroid of the body in this case when it is fully submerged. Okay. Whereas if we have an object which is partially submerged, like this one, now suppose this is submerged, this much part, then the buoyant force will act through a center of buoyancy, which will be the centroid of the submerged portion of the volume. So in this case, the center of buoyancy this will be the centroid of the submerged portion. Because again, the general definition is that the center of buoyancy, it is the center of gravity of the equivalent volume of fluid displaced. Okay, so at a practical level, this concept of center of buoyancy or buoyant center is important in understanding the stability of a floating object. You will intuitively understand that the lower the center of gravity for a floating object like a ship or something, the more stable it is for a situation where it tends to rock, it tends to tilt a little bit because of wind conditions, etc. Now, whether that tilting is going to make it topple or not, that depends on the relationship between the buoyant center or the center of buoyancy and the center of gravity. So stability of a floating object. So let's say we are taking two examples of floating objects, which look something like this. Now, in one case, let's say we have loaded the material in the top with some mass. So the center of gravity is comparatively higher up. So the weight is, let's say, acting through this kind of a point. So this is our center of gravity. And while it is floating in the liquid, the center of buoyancy is somewhere here. It is the centroid of the submerged part. So I'm just showing a very extreme situation. Okay, so this is in the normal floating condition, the vertical line. Okay, so we have buoyant force equal to mg, and the net torque about the center of mass or center of gravity or whatever is 0. Okay, but if this now tends to tilt like this, what will happen if this tends to tilt? So the moment this kind of thing tilts like this, you will see that the buoyant force is acting through this point, and the center of gravity is here. Okay. So in tilting by clockwise angle theta, now the buoyant force is creating a further torque clockwise with respect to the center of gravity or with respect to the center of mass. So this is a torque because of buoyant force. So it is what we call a non-restorative torque. It doesn't try to restore it back. So this is a highly unstable kind of equilibrium. Even slight disturbance will cause it to topple. So it will make it topple. Or gives it a tendency to topple. Okay. On the other hand, if the same thing, we had loaded the mass from below. So let's say this is like the cross section of a ship. Obviously, the shape will not be perfectly rectangular like this, but okay, but it's loaded from the bottom. So now the center of mass is coming comparatively lower because of that. So mg is acting through the center of gravity like this, and buoyant force is acting through the center of buoyancy somewhere over here. Okay. So this is in equilibrium. Now, when this thing tends to rotate, like this, you can see the buoyant force is acting through such a point. The weight is acting through such a point. So as this is tilted through an angle theta like this, about the center of gravity or the center of mass, the buoyant force is creating a torque which is like this. It's opposite in nature. So it creates restorative torque. It'll have a tendency to prevent toppling. So that means that this is a stable kind of equilibrium. So this is what is desirable for floating object stability, and this is what is undesirable. So that plays a major part in shipbuilding. In fact, at graduate physics level, there is a more complex term called meta center, which is basically the point at which the line joining the center of buoyancy and the center of gravity meets with the vertical symmetry line of the mass. Okay. But anyway, that is not part of our syllabus here. So this is like the practical importance of the concept of center of buoyancy. Okay. Now, of course, we can get adapted questions in which we have to apply our knowledge of rotational mechanics and torque, etc., to understand either rotational equilibrium or to understand a situation in which torque is causing a body to rotate underwater. Yeah, so Aditya, that's correct. Okay. Yeah, Vinita, I'll scroll up. And Nikita, to answer your question, the center of buoyancy will be calculated by just this simple concept that the center of buoyancy is actually the center of gravity of the equivalent weight of fluid displaced. So you just see that whatever part of the body is submerged, that volume is, now imagine an equivalent volume of fluid. So where would the center of gravity of that volume of fluid be? It would be at the centroid of the submerged portion. Okay. So that is why whether the body is fully submerged or it is partially submerged, it is always at the centroid of the submerged portion of the body. So in this case, it is the centroid of the full body only because it's submerged. Whereas in the second case where it's partially submerged, it is the centroid of the submerged portion of the body. Is it clear now how we'll find the center of buoyancy? Okay. Okay, Vinith, this is the portion you wanted. Okay, so now let's see a typical JEE level question involving this center of buoyancy concept. Okay. So for example, now we have this situation. This is, let's say, a water tank. Okay. And initially we haven't filled water. Now what we've done is we've taken a wooden plank, okay, and it is kind of hinged at one side. Now as we start filling water, the hinge will not allow the plank to float up, but instead the plank will rotate about the hinge. So imagine that the plank is, or the log of wood is hinged at this corner over here. So as we fill water in the tank, this is what we'll observe. With the level of water rising, this is a hinge about which the wooden plank can, rotate freely. So as we fill water in the tank, instead of floating up, even though the wood is lighter than water, because with that hinge, it will come to this kind of position. Okay. So if this is a wooden plank of uniform cross section, and length equal to 5 meters, density of wood, let us say 0.6 gram per cc. Now we have to find out up to what level we have to fill water so that the hinge plank is in equilibrium at theta equal to 37 degrees. So find the level H of water of density 1 gram per cc such that the plank hinged at the corner, say O, this corner here is O, okay, is at equilibrium at theta equal to 37 degrees. Okay. So as you can see, this becomes a static equilibrium of rigid body kind of problem. So it is about not only balancing net force, but net torque being zero. And particularly when you have a hinged body in equilibrium, then you want to balance the torque about the hinge, because the reaction force at the hinge will adjust in such a way that the net force will anyway be zero. But that reaction force at the hinge doesn't create any torque about the hinge. So the equilibrium will always be in that position at which the other forces, not the hinge reaction force, but the forces other than the reaction force at the hinge, their torques are getting balanced. Okay, so to understand torque balancing, you have to understand the point through which the buoyant force acts. And to understand that, you have to understand the center of buoyancy concept. So just try this out. We'll discuss. Okay, so let's discuss the concept here. So if we think of type of free body diagram kind of situation, so we'll see here that suppose this is the level of water to some height h. Then the buoyant force will be acting through a point like this. So the center of buoyancy, if this point is, let's say B, and this point is A, the center of buoyancy will be the centroid of the submerged volume. So submerged volume is the portion OP. Okay. So the center of buoyancy will be the midpoint of OB, that part of the length. Whereas the gravitational force will act through somewhere here. Center of gravity will be obviously midpoint of OA, centroid of the plank. And also the buoyant force will be equal to density of water into volume of the submerged part. So let's say the submerged part is of length x. So it will be x into some area of cross section into G. Whereas mg will be density of wood into L into A into G. Because the length OA is equal to L. So the length of the plank. So now all you have to do is balance the torque. And of course, in this case, we will see that the buoyant force will probably exceed the weight. So there'll be some reaction force also acting at the hinge, which will be like this. So buoyancy will be creating this kind of a torque. Okay. Gravity will be creating this type of a torque. And the two should cancel. So net torque about the hinge at O should be 0. So that means the buoyant force into, now whatever this moment arm is, we'll calculate in a moment. Suppose this is R1. This is creating a clockwise torque. This should be balanced by mg into this moment arm. Which is creating the anti-clockwise torque. So now all this information has to be used. Okay. So as you can see, if you draw the line OB, its vertical projection is H. And this angle is theta. Okay. So you have H by X is equal to sine theta. And you can also see that the center of buoyancy being here, you also have So R1 should be two by three H. Just check my calculation for theta equal to 37 degrees. Just check this calculation I've done over here, but okay. Now on the other hand, R2. So for R2, you have to understand that this distance OA is equal to L. Okay. So R2 is equal to L by 2 cos theta. That should be 2 by 5 L. Okay. So now further, we can first write it like this, that this is buoyant force into x by 2 cos theta, and this is mg into L by 2 cos theta. So that's probably an easier way because cos theta will cancel out. Now buoyant force itself is equal to how much? It is density of water into x into A into G, is density of wood into L into A into G. So ultimately what we get is that density of water into x square should be equal to density of wood into L square. So x should be equal to L into square root of density of wood divided by density of water. So x should be equal to L into square root of 0.6. Okay. And h is equal to L, x sine theta or 3 by 5x. So I'll get like this. Or you can say that h should be equal to so this is the answer you should be getting. So hope you understood. In this diagram, I've taken this distance from here to here as x. Okay, hope the calculation is clear. Okay, so hope this calculation and this question is clear to all of you. Okay. Now let's go back to pressure gradient finally and look at one more interesting concept in pressure for pressure gradient. So let us see pressure gradient for a fluid which is in a non-inertial frame. In an ideal fluid at rest or static, in an accelerated frame. Okay. So basically in non-inertial frames. So of course the trivial case of this is when we have vertical acceleration. It just kind of changes the effective value of gravity. So for example, if we have an elevator which is either accelerating vertically upwards or downwards, whichever be the case, vertically upwards, it will increase the vertical pressure gradient because pseudo force will act downwards. So inside this we have a tank which is having fluid. So whether we observe this from the point of view of the person inside the frame or even from the inertial frame in the ground below, we'll get the same result that if we take our vertical axis to be the y-axis and the horizontal plane to be the xy plane, we'll get again del p by del y will be minus rho of this time E naught plus G, whereas del p by del x will be equal to del p by del z, which will be equal to 0, which is a horizontal gradient. I'm not getting into the detailed derivation of this. You have to just understand that if you think of the free body diagram in the non-inertial frame or even the inertial frame, okay, of a volume element, you can understand this easily. Okay, so just make a quick note of this. JP, what are you doing up there? Why are you sitting there? What? Right. So when you look at this kind of a volume element, which is of vertical thickness dy in the non-inertial frame going upwards, it's at rest. So you can see that there is weight and there is pseudo force, which has to be balanced with so dp into a will become minus of dm into g plus a naught, and this dp will write as vertical pressure gradient into dy. So this result will give us this. Same thing, if the elevator had been accelerating downwards, then the pressure gradient would have become, vertical pressure gradient would have become minus rho into G minus A naught. So interestingly, for a freely falling tank, the pressure gradient is 0. Okay, now let's look at the more interesting case of horizontally accelerated tank. So let's say we have a situation like this, that an open tank is accelerated horizontally like this at A naught. So first of all, the interesting thing we'll see here is that the water on its surface or the liquid will not be horizontal anymore. The pseudo force is pushing it back against the acceleration. So the surface of liquid will be inclined to the horizontal. So here if we take the horizontal axis along which the acceleration is happening as our x-axis, we'll see that there'll be a horizontal pressure gradient along that axis of minus rho a naught. There'll be a vertical pressure gradient of minus rho g. But of course, the z component of gradient will be 0 because there is no pseudo force along the z-axis. So this occurs due to pseudo force on the liquid along negative x-axis. This occurs because of gravity along negative y-axis. That kind of situation. Okay. So the idea is now if we look at a volume element which is of thickness dx like this. Okay. This coordinate is x. Now we look at it from the point of view of our non-inertial frame of the tank. Okay. And we consider only horizontal forces on it. So that volume element has a volume of A into dx, where A is the area of cross section. So we'll see that the pseudo force acting on it is in this direction. I'm not worried about the vertical forces. I'm not considering them in this diagram. I'm only considering the horizontal forces. So P is the pressure at x equal to x, whereas P plus dP is the pressure at x equal to x plus dx. So from this, the change in pressure is horizontal pressure gradient times the change in the x coordinate. Okay. Now, in this frame, in this non-inertial frame, this volume element will be seen to be at rest in equilibrium. So forces have to balance. So balancing of the forces will show us here that minus dP into A will be equal to the pseudo force. So minus dP into A will be minus rho A dx, that's the mass, into A naught. So dP is equal to minus rho A naught into dx. So further, so this is how you can demonstrate that the horizontal pseudo force creates horizontal pressure gradient. Now, whereas in the same non-inertial frame, if you consider a vertical element and you consider only vertical forces in your FPD, so then you can show that the gravitational force has to be balanced by the force due to pressure difference. the same thing over here. In this case, the dp will be del p by del y into dy, and doing all this you'll be able to show that. So here you can see that inside the liquid, the pressure is a function of x and y coordinate both. So now, for example, if I consider a point like this over here, and I consider a point like this over here, such that they are at x1, y1, x2, y2, then to calculate the pressure difference between A and B, I'll have to consider both the vertical and the horizontal gradient of pressure. So we'll come to that, but first, just make sure you're clear with this concept set over here. I'll tell you an easy way to remember this also. Okay, so now, for example, here, if I'm comparing these 2 points A and B, E to B, the pressure difference, that is pressure at B minus pressure at A, will become del P by del Y times delta Y plus del P by del Y, del X times delta X, because both of these are uniform. Okay, so because they are uniform gradients, so we can write this relation. For those 2 particular points that I've shown above, the pressure difference will be minus rho g into the change in y coordinate minus rho a naught into the change in the x coordinate. Okay, so this also brings us to the whole idea that the angle of inclination for the top surface of the liquid with respect to the horizontal, that will be given by the familiar formula of tan theta equal to a by g, or in this case a naught by g, we can say. Now this surface is inclined like this, we know, because the tank is accelerated like this. Now, with respect to the horizontal, if this angle of inclination is theta, is a very easy way to find this angle of inclination and show that theta is equal to tan inverse A by G. For that, you have to just consider, for example, this point A, this point B, and this point C. So, if this height difference is delta H, okay, between A and B, and the length of the tank here is L. So we know that del P by del X is minus rho A naught. So we can see that pressure at C minus pressure at B will be equal to minus rho A naught into L. So that means the pressure at C, oh sorry, minus L, because the position of C with respect to B is at a change in X coordinate of minus L. Okay. So now pressure at the point B should be atmospheric pressure. Whereas using the vertical gradient, you can see that so the pressure difference between the points C and A is rho G delta H. So the pressure at the point C is also equal to atmospheric pressure plus rho G delta H. So if I compare these two equations now, it's easy to show that tan theta is equal to A by G. Okay, so the easy way to remember this, which I was telling you about, is that if you are analyzing your physics from this frame, which is the non-inertial frame, traveling at A naught, then in your frame actually you see effective gravity like this. This G prime is root of this, like the apparent gravity. Okay. And that apparent gravity G prime, you will remember, is inclined with respect to the vertical at that same theta. So what happens is that the surface of liquid here is going to be inclined at 90 degrees with respect to this, the theta of G with respect to this. And that is why the pressure gradient will have a horizontal component as well as a vertical component, because your effective gravity G prime is having a horizontal component of A naught, okay, pointing along the negative X direction. So your pressure increases with the negative X direction or against A naught by a factor of rho A naught. Whereas your effective gravity G prime has a vertically downward component of G. So accordingly, your pressure increases with depth by a factor of rho G, by a rate of change of rho G. Okay. So that is the simple sort of intuitive way of remembering this result. Okay. So we're now done with the concept set and the basic types of problems of hydrostatics. Okay. So next lecture, when we get JEE Advanced type questions in hydrostatics, and after that we will be moving on to hydrodynamics. Okay. So next session we will do some more questions in hydrostatics and then move on to hydrodynamics. Okay, Aman, I'm going back to that question and explaining it again. That rubber ball problem. In that rubber ball problem, see what is happening. The ball looks like a solid ball from outside, but when you cut it, you can see that it's hollow. It's a thick shell which has inner radius R1 and outer radius R2. So what is the mass of rubber? It is density into volume of rubber. So see this expression here, volume of rubber is basically the volume of the shaded portion here. No? So is this. It is not 4 by 3 pi R2 cube. It is R2 cube minus R1 cube. The air inside is of negligible mass. So the weight of rubber is equal to this quantity. Whereas the submerged portion, how much volume of water it's displacing, that is half of the outer volume. So that's 0.5 of 4 by 3 pi R2 cube. So that is why your final answer for density of rubber comes out to be this factor of sorry, this will not be 8 by 7. It will be
4
4
by
by 7. Yeah, my mistake.
Yes, sir.
There's a
That's
0.5 into this. So just make a correction here. This is 0.5 into this. So the answer should come 4 by 7. Okay. So that is approximately. Okay. But it doesn't come out to be 0.5 because 0.5 would have been the case where a solid rubber ball was floating with 50% submerged. This is hollow ball, so its average density is somewhat greater than this. Okay.
yes.
Okay, so this is clear now. Okay, so with that we come to an end for today's lecture. Okay. Last
Thank
slide
you,
once again. Okay, okay. Yeah, Naman, I'm
Thank you,
showing
sir.
the last portion also for the horizontal pressure gradient concept once more. Right, so that's it for today, people. Wish you all the best. Thanks for attending.
Thank you, sir.
Thank you, sir.